Slope fields, essential question. Can I construct a slope field and graphically solve a differential equation with an initial condition? What is a slope field? Well, first let's start with a differential equation. In this differential equation, I'm going to find the solution, and it's going to be x squared plus c. This represents a family of antiderivatives, which is what's being shown here. When we look at a slope field, we're not going to look at the whole curve. We're going to look at a suggestion of the curve. What's going to happen is we're going to be looking at little tangents at different spots on the coordinate plane that suggest what the solution looks like. Let's go to the next slide. So the solution set is a family of antiderivatives, and the slope field is actually a great way to visualize this family of antiderivatives with little tangents called isoclines. We can then interpret graphically the solution, so we can see where it's increasing, where it's decreasing, and where it may have a minimum or a maximum. When we use our calculators, we're going to be able to see slope fields in this manner, where a lot of points have a little tangent line to suggest the solution. Let's go ahead and practice making these little isoclines. So this is a slope of 1. How do we make a slope of 1? I usually just think of a 45-degree angle. When I want to graph a slope of -1, it's a 45-degree angle in the other direction. When I want to graph a slope of 2, I make sure it's steeper, -2. Again, that's steepness, but in the other direction. A slope of 1/2 is going to be closer to a flatter than a 45-degree angle, so I'm going to make it like this, and 1/4 is even flatter. We can draw it that way. All right, let's go ahead and practice creating a slope field with these points right here. Okay, the slope here is 2. So I'm going to make a steep slope of 2 at every one of these points here. Slope of 2. And so all these tangents are really parallel to each other. Now let's go ahead and solve, because this is not a hard one to solve. This is going to be 2x plus c. So does this suggest to you a linear function? I hope it does. All right, let's take a look at this slope field. Now this says that the slope depends on the x value at the point. So all of these right here have the same y value, and the y value is 1. So we're going to make a 45-degree angle. All of these points have the same y value, which is 0. All of these have the same y value, which is -1. All of these have -2. And all of these have +2, which is a steep slope. So notice that along the row, the slopes are all the same. Now let's take a look at this. When x is equal to 0, all of the slopes only depend on x, and they'll all be the same. So when x is equal to 0, which is all of these points have x equal to 0, it'll have a slope of 1, which is about a 45-degree angle. Notice that the columns are all the same now. All of these points have something in common. The x value is 1. So when you take 1 and add it to 1, you're going to have a very steep slope of 2. And -1, if you put -1, all these points have an x value of -1, and that's going to yield a slope of 0. So I hope you notice that when it depends on x, the columns are the same. When it depends on y, the rows are the same. All right, now here's where x and y, both x and y. So let's go ahead and I look for features that make sense to me. Whenever x is equal to 0, you have an undefined slope. Undefined is a vertical slope. So I know when x is equal to 0, which is all of these points right here, then I know I have a vertical slope. So I'm going to make a vertical slope on each one of these. Now I'm going to just use this point. This is the point 1, 0. So I'm going to have a 1 here, and I'm going to put 0 in for my y, and so that's going to make a slope of 1. Now this is the point 1, 1, 1. So I'm going to put 1 down here and 1 up here, and that's going to be a slope of 2. This is the point, 1, 2. So I'm going to put a 1 down here and a 2 here, and that'll be a slope of 3. This is 1, negative 1. I'm going to put negative 1 over here, and that's going to be a slope of 0. I'm going to have 1, negative 2, and then I put a negative 2, and this is going to be a slope of negative 1. And you do about the same thing on this other. You just go 1 point at a time and substitute. Now on this one, I try to look for a feature that'll help me. X is equal to y. When x is equal to y, then I know that the slope is going to be 0. So at 0, 0, it's 0. At 1, 1, it's 0. And at negative 1, it's 0. So I can do that. Now I just have to go 1 point at a time. So I'm going to use the point 0, comma 1. So this is 0, take away 1, and that'll be a negative 1. Then I'm going to use 0, comma 2, and then that'll be a negative 2. Over here I'm going to use 0, comma negative 1. That'll be a positive 1. And 0, comma negative 2, and that'll be a positive 2. And we go through all the points and we substitute in that same way. All right, so I hope you saw that when the differential function is a function of only x, like this one right here, when it's a function of only x, then the isoclines are the same on each column. When the differential equation is a function of only y, which it was right here, then the slopes of the isoclines are the same on each row. Now, if it's a function of x and y, check what conditions make a slope of 0, like I did. When you have values of x and y, what makes the denominator 0? Because when the denominator is 0, the slope will be undefined, or it'll be a vertical slope. Check what happens to the slope as x or y gets large, and use the differential equation to determine which quadrants the slope should be positive or negative. These are all little hints on how to do this, how to recognize them. All right, let's see if you can use some of these hints and you can match the slope field with its differential equation. Stop the screencast and see what you can do. And here are the answers. I noticed that this was sine of x, and I can find the antiderivative very easily. It's negative cosine of x plus c, and this looked like a negative cosine to me, so I picked that one. And over here, I noticed that at y equal to 0 and y equal to 2, that I had horizontal lines, and so this allowed me to use this one. I thought that this matched really well with that, because when y is equal to 0, we have horizontal tangents, and when y is equal to 2. And over here, I noticed that when x is equal to y, I noticed that the slope was equal to 1, and I saw all of these as 1, and I could see a negative 1 going over here. So these were some of the hints I used for myself to help. Okay, try again. Go ahead and stop the screencast and see if you can match these. And here are the answers. All right, I'm looking at these two, and these two all have the rows that are the same. And no, not that one. This has the rows that are the same. When the rows are the same, then I know it's dependent on y only. And I also noticed that at y equal to 1, it was equal to 0. This one, I found this, and I know the antiderivative. I can do that in my head, e to the x plus c. And this looked a lot like e to the x right here. Over here, I knew this depended on x and y. So I was looking at two of them that depended on x and y, and that was this one, a, and this one, d. And I think I had already used A, so I thought D was going to be this one. And you can check out when x is equal to 0, then I knew that it was going to be equal to y. So all of these, whatever y was, that was its slope. And when y is equal to 0, I noticed that the slope was 2x. So when y is equal to x, then along this x-axis I knew that slope depended on 2 times whatever the x value was. Now the only one we didn't talk about was this one. And I took this differential equation and I actually found the antiderivative, which is a parabola, and it's pointing down, and that's what I see right here. So that's why I was able to assign that one. Okay, let's talk about curve sketching. So we have this family. Can we find a particular graph? And so here's the point right here, and what we would like to do is we would like to follow this. Now this looks like a parabola because it's going down and then up. So we're going to use this to help us, and what you're going to try to do is make sure that these isoclines look like they're tangents for that line, for that curve. Okay, over here I have this, and I'm just going to try to follow along, making sure this is looking like a tangent, and we go ahead and do that. And it's a good strategy to try to go between the isoclines so that they appear like they're tangents. All right, your turn. Go ahead and use this and see what you can draw. And here's the answer. I failed to find this other one, which I'll do right now. And you have one more. And here's the answer.